Okay, hello. Welcome. I hope you've had a good week. So let's pick up where we left off. Um, as you remember, now we've got a couple of cool little things. We've got a triangle, we've got a quad, and we render those. And so if you recall, this is what we get. Cool. Right now these don't do anything. So for the most part, in the last lecture, we went through how to create a mesh class, and obviously a lot of this is going to be done by the underlying framework for you, but to really understand how to do this, in particular with the assignment that you have in front of you, it will be around creating a variety of different meshes and a variety of different kind of primitives. And while those primitives are going to be made up out of triangles and out of quads, to understand how to do that, to make something more complicated, say a cube or a sphere, how would you go about doing that? And so let's kind of jump into it and take the mesh class that we developed in the last lecture and expand that into effectively a cube. So if you recall, we set up a couple of objects here. And let's make it really simple, like we were doing before. Mesh MP cube, and set up an null pointer. Great. And then let's do the same thing here, right? MP cube. And let's kill these guys for a minute because we don't want to deal with that. And then finally, cube. And then one thing we don't have here is we don't have a make cube function, which is going to blow us up. So let's go open that up here. Let's keep it open. So we're missing a make cube function. So let's go, and again, to remind you of what this is about, these are factory methods. But you'll notice that it gets kind of annoying, right? Like these are all taking a size, right? I can do another my mesh make cube float size. It's getting really annoying. There's like 3 of these, maybe there'll be 4. I want to do it a little bit more eloquently. So what I can do is I can create a my mesh. This is what's called a enum. So type def enum class, and then we're going to call this types, and then we're going to say triangle, quad, cube, invalid. We might need to just do it this way. Great. You can also type def it. You'll see this pattern that looks like this, and then this is a pretty common one. And then what we'll do here is instead of, we'll keep these functions because they're convenient. But we're just going to create a make, and then we're going to pass to it a type. Cool. You'll notice we have 2 missing functions here. So to do that, why you do me like that? All right, so then we do this, and we do p mesh equals null pointer, and then we return p mesh. So already we have a functional thing. And really all we have to do is then we set up the mesh type, and now we just fill it out. my mesh type. Let's start off with triangle. Then we have quad. Then we have cube. Cool. So we're already off to a pretty good start. Let me zoom in a little bit more just to kind of help you guys out. And now all I have to do, right, is p-mesh. Cool Hebrew. I'm gonna turn off that thing. Yeah, I can also do it like this, right? No, doesn't show up in the. Just to prove I'm not being weird. No, I'm not gonna do that. I'll do it here. See? No. Great. Okay, just to prove I'm not strange. Probably I'm a little. Okay, so back to this. We've created what's called this factory method. And in here, now we can just say pmesh. Thanks. Pmesh is equal to mymesh make triangle and size, which we forgot to pass here. Cool, and now we can do the same thing for cube, quad, and for cube. And notice, right, we can do case mymesh type invalid with a fall through to the default case. And here we would throw some kind of error. Mesh equals null pointer. Error. Whatever. We won't do that here. But either way, you can kind of see how this simple thing, every time you want to add a new type of object, all you would have to do is create a new one of these, right? And then create the applicable object. And one final thing we want to do here is these are now going to be private, so you can no longer access them. You can only access this one. And so in the app class, you'll notice makeCube is going to give me an error. Function blah 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 is inaccessible. But I don't have to do that. I can do make, and then I can do mymesh cube type cube and bang. Great. Now the issue is makeCube doesn't do anything at the moment. So let's follow in the footsteps of our previous thing. Init quad. But here's the issue, right? So init quad, let's go to the definition, void init quad cube. I'm going to do it in kind of a weird way. So this might be interesting for you guys to sort of see this in action. So I'm going to go to make cube and then init cube. And right now, let's just run it for sanity's sake to make sure the code works. So right now I expect a quad, just like we had before, because it's just going to show up, you know, like it's just going to, well, actually it's going to give me a failure because make cube does not exist. Oh, init cube does not exist, which is something we need to resolve. Okay, and this is going to do nothing, so we're going to get nothing. Probably going to get some kind of big error because, okay, maybe not. Cool. Now, there's a couple of options, so let me do it the traditional option. I'm just going to copy this, literally the same as making a quad, and you can notice, okay, so now we've got a top left, top right, bottom left, bottom right, and so on. Let's run that and see what happens. Cool, so now we've got a nice little guy there. There's another thing that we can do that I want to kind of bring up. So this is going to require us to do a little bit of a change to our architecture. This is a bit of extra, so don't necessarily feel like you need to understand this all the way. So one thing that a cube has is a depth. And so already we have to, we just copied this code from the quad. And so what we need to do is we need to extend that out into the z dimension, right? So this is not top left and top right and bottom left and bottom right anymore. There's actually two of these, right? If you think about a cube, there are 8 vertices, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, and now we're going to call this, we're going to rename a lot of these actually. So this is going to be top left front. Okay, and this is going to be also top right front. Actually, let's do this. Let's make our lives a little bit easier. Okay, we're going to copy this. Then we're going to add front to all of these. And now when we paste it, we still have the old one, and this is going to be back. And then finally we're gonna do this. Okay. And so this is going to be one face. This is actually the front face. And if you think about a cube, there are 6 faces, right? So let's go 1, 2, 3, 4, 5, 6. 6 faces. And what are they? We've got the front, we've got the back, we've got the left, we've got the right, and we've got the top and the bottom. And now this is where things get a little bit annoying. We have to sort of start to figure out how everything fits and how everything works, right? This is going to be a really eloquent packing, right? As compared to another technique that I'll see if I have enough time to kind of go through. So the front face we've already done, and if you recall, we want a counterclockwise ordering of the vertices. So we've got the top right, the top left, the bottom left. We've got the bottom right, the top right, and the bottom left. So these are always going counterclockwise. So with the back face, that's not really true anymore, because first of all, we want back. We want to use the back vertices, which we'll deal with in a second. And then, but the problem is the top right in the back, top left in the back, that's going to be inverted. That's actually now clockwise. And so we almost want to flip these, where we go top left, top right, bottom left, and that's going to go clockwise to me, but if I'm facing the other way, that would be counterclockwise. Weird. A little bit kind of hard to visualize, but that's sort of the idea. And then same thing here, we almost kind of want to invert those, where the top right, bottom left, again, that's clockwise, but I want it to be I want it to be clockwise because it's backwards. So cool. So let's leave that off for there, because now we actually have to position these in 3D, because right now they're all in 2D. So the top left front, all of the front ones, I can simply just give it size here, because it's going to be out in front. Now in the back, though, it needs to be negative. Cool. Now before we actually do anything, let's actually kill these for a bit. We're going to add one face at a time, but you'll notice something very quickly that is impossible. Like, it's going to be really difficult for us to tell what's going on, because we neither can see the, so if I, for example, do this and I render it, cool, it's still the same thing, right? If I add the back face, it's still the same thing. If I only render the back face, it's not going to be the same thing. It's going to be ideally nothing, because it's not facing us. So how do we deal with that? Okay, well, let's take a quick look at our code. We need to open up our code here. Let me do this off screen. So drop off. Oh, right, I'm actually in my dev. And include GL, oops. No, where is it? Nope. Here we go. So we are using the which shader are we using again? Always forget this. All right, let's figure it out. Let's figure out what is the this is such a big font. main, goes to new application, init, get instance, init, set window, read config. Window. Oh, that's right. I'm an idiot. We're doing this here. We're using basic color and basic color. Great. So, all right, let me open this up. The fragment, actually we're more interested right now in the vertex. So you'll notice that the transform is this matrix that we're passing in here. And where are we setting that when we're actually rendering the transform? It doesn't look like we are yet setting that at the moment. So let's do that. So now, before we draw, what we want to do is we want to be able to set that transform like we were doing before. Now, if you recall, the way we do that is we want to set this uniform. And to do so, I'm going to open up our old trusty code here. That's going to remind me of the calls to do that. And so when we did that originally, we would effectively get the MVP ID by way of get uniform location, as you can see here. And then we set that to this matrix of the model. So let's go ahead and copy that really quickly. And you'll notice that all this stuff is broken. And so what we need to do is we need to add in those header files that we had previously, all of the GLM things. Great. We're going to add that to my mesh. Oh, it looks like we already have quaternions, all that stuff here, so we don't need that. Okay. Fine. All right, we're missing a different function. We're missing the GLM value. Where do we define GLM value? I see. That's not the problem. Okay, so the other thing, let's just really quickly copy these as a basis. And we're missing the model matrix, which we'll deal with in a second. And all we're doing is really just passing this transform in there. Great. Cool. And it's not MVP, it's transform, so we're going to change that to transform. Otherwise, this code will not work. And so now when we run it, hopefully we'll see the same thing as before. Great. Now, I want to start to rotate it around, because you can imagine a cube is inherently a 3D object. And so with a 2D projection, you can't see the whole cube. You want to be able to see all parts of it. You want to be able to rotate it around. And the way you would do that is you would rotate it. And so the bit of here we can mess with is the model matrix. And we can actually go and use GLM to create a rotation matrix about, let's just mess with Z for now. vector. I remember I had this issue last time. Okay. Let's just do this. I just want the rotation transform. Sorry about that. Sorry about the wait and me kind of bumbling through this. Let me figure this out. I remember doing this earlier. Okay. There. Let's grab this on its own. So in this case, rotate around the identity, theta, and then the we're going to be going about y. Let's go 15. Okay, and what this will do is we'll rotate about y, which is not exactly what I want, but that's okay. Cool. And let's create a static float theta is equal to 0.f, 0.f, and then theta plus equals to 0.1. And so every time this hits the draw, it's going to rotate a little bit more. A little bit too slow, it looks like. Oh, and I'm going to have to actually pass it in. You'll notice that now it's kind of rotating around, and so that other face is now correct in that it's our other cube face, which is nice. Now you'll notice also that this cube's a little bit oblong. It's not really a cube, it's more like a rectangle. But if I go and I resize this window, you'll notice the way I resize it is ultimately going to bring it and make it look more and more like a cube, which is a problem that we'll deal later. We're not dealing in projection matrices yet. But you can kind of imagine the issue here, where the projection matrix right now does not take into account the window size. So we'll deal with that a little bit later. So cool. Now we've got this relatively simple rotation, but I also want to see the top, which is important. Right now we're rotating about y. And so another thing I can do is I can add, I want to rotate it about x so I can see the top of the cube. You'll notice something happen when I do that. And this might not work because it's only going to rotate about X. And this is, I think, an important thing to note. You see, you have to sort of combine these. You have to sort of create a composition of these matrices. And so I'm going to apply M4 times this. There's another way to do this as well, which is I can rotate it like that. Or I can not do it that way, and I can literally just multiply the matrices. Either way, it's sort of producing the same effect. Until we get the matrix, the projection matrix in there to look a little bit more normal, it'll be kind of hard to see the real kind of cube structure. But for the time being, what we'll do is we'll rotate just by the particular angle so that we can see, or the particular axis so that we can see the faces that we want to see. So right now we're rotating by Y, and it's going to rotate it kind of around, and so what we expect to see is always a new face facing us. Okay, cool. So let's go and now create the left face, because we have the front and the back. And the left one should be the first one that shows up when we're looking at when it's rotating. And so if you can kind of think about the left face, there's going to be 2 in front and 2 in back, but they're all going to be to the left. And so that's going to be our first hint here. So anytime we see right, we get rid of that. Left, left. Huh. Well, we've got top. What am I missing? Vertex. Clearly, that's the problem. Okay, great. So now we've got top left front, top left front. That's not good. And then bottom left front. And so what we want is we want counterclockwise, so top left front to the bottom left front. And so we want to go top left front, bottom left front. That's going to create the bottom triangle. And no, we want to go opposite. We want to go top left front, bottom left back, also that's the T, and bottom left back, and then bottom left front, and that should create a counterclockwise triangle. That's going to be the bottom triangle. So maybe we want to by the convention above, we want to do the top triangle first. And so starting at the top, the bottom left front, well, we can't be bottom left, we want to be top left. Top left front, and then we want to go counterclockwise. So actually, why don't we start from the back? Top left back, top left front, and then bottom left back. And that should give us a triangle, the top triangle. And let's see if that's the case. Great, now you can see that top triangle, but the bottom triangle isn't showing up, which is no good. And you can see it's actually showing up in the wrong place because it's facing the wrong way, which is no good. So the bottom triangle is not working, and so what's wrong? Okay, so let's take a look at it. Top left front, top left back. Well, that's not right. We want to be bottom left back. So let's see. Let's make sure that our top triangle is actually working correctly. Okay, no. So our issue wasn't that wasn't working. It's just this one is not working. So top left back, top left front, bottom left back was not working. So what we want is maybe if we flip these guys. There we go. Now we want this one, and that one. And so let's go back to here. And top left front, bottom left back, bottom left front. But that's going to be counterclockwise. So this should hopefully work. There we go. And now we've got that extra face. And you'll notice here, we won't see anything for a second because there is no face facing us. Great. Now let's do the right face. What's really fun is you can actually kind of use your work as you go through this. So right face. So first thing we know, none of these are going to be correct. Yeah, everything's going to be on the right and no longer on the left. Cool. Now the issue is if it's on the right, then now you want to flip it around. So the top right front, top right back, bottom right back, it's going to be clockwise, right? So if you flip them, generally speaking, if you just flip the middle one, it should do the job. And what we're looking for is we're looking for that final face on the back side. So we expect to see another thing there. And there you go, there it is. Now finally, we want to see the top. Now the top we're going to have to rotate in a different way. We're going to have to rotate up because otherwise we won't be able to see the top faces. And so let's kind of try to intuitively figure out what the top face is. And so first of all, there's going to be no bottom. There's only going to be top. So that should be easy. And then if we're looking at it from the top, you can kind of imagine we want to do the bottom triangle, the top triangle first, which is going to be the back left, or back right. So back right, back left, right, and then front left. And that should give us the top triangle. So let's see if we see anything. It's going to rotate down. We expect it to see one triangle on there. There we go. Cool. Must have not turned off. Oh, well, there you can see what happens when you rotate it about an arbitrary axis. Okay. Cool. So we got one of those triangles, and now we want the other one. We want the bottom one. So we want top right back, and then top left front, and then top right front. Right, we're going this way. So let's see if that works. Let's see if we get a top face to our cube. Nice. Looks good. And we expect to see nothing down there because there is nothing down there. Okay, so now it's just to do the bottom face again. Rinse, repeat. And let's do that trick again where I just flip the middle. And then all I have to do is switch it from bottom to top. And now we expect to see a face on the bottom as well. Cool. And now, for all intents and purposes, we have a full cube. So if I go and I add this plus that, let's add in a little bit of randomness. Hopefully we'll see a little bit of randomness as well. Not much, but cool. Whatever. Not so helpful. But either way, now we have this nice little thing. Now it doesn't really look like a cube, and that's largely because we're not doing perspective mapping of the scene. And so what we can do here, and there's going to be a better way to do this in the future, right? Like your application has a camera that underlying, so I'm not using this code, I'm using this. You can actually find this in the app main, right? Your camera manager, and what you want is to then use that in your mesh class. And I'm not going to go into too much depth on how to do this. This is a deeper subject. But let me do this where I can do auto camera manager, right? And we can go open this up and check out the camera manager and what it gives us. And we can get the projection matrix of that, which is what we want. And allegedly, this should give us the like a better, oh, all gone. Okay, I'm using a I don't have much knowledge in how to do this yet. I haven't played with this code very much yet. This is largely Alberto's code. So I'm not going to pretend to know what I'm doing here. Let me just write my own projection matrix. Should be easy enough. So GLM provides you the projection matrix. Let's look that up a little bit. There we go. Perspective, FOV. And so our FOV is going to be, call it 60 degrees. And then our aspect ratio we'll get in a second. call it this for now. And then our near is going to be 0, 1, and then our far is going to be 0. So I'm not going to go into too much detail on this yet, but in short, I'm applying a perspective matrix to this sort of over here. So the projection is going to apply then. So the model is going to get rotated, and then we're going to apply the view, which currently is a identity, and then we're going to apply a perspective to that. And allegedly this should work pretty okay, or it won't, because we also need to actually create a view matrix, because right now we are inside of the cube, which is no bueno, which is probably why the camera before didn't work. And so just simply, I'm going to take my view matrix and I'm going to turn that into a translation of there we go. GLM mat for 1.0, and then GLM FEC 3. We're going to go backwards 10F. Let's see if that works. Great, now the cube is all the way over there. Let's maybe get a little bit closer. Great. So now you can see it's all sort of screwed up now. That's because our FOV is quite, wide, and then our aspect ratio is 1, which is no good. So actually, I'm going to go back to, let's save this, but I'm going to go back to using the camera manager. So let's do this, camera, auto p camera manager, camera manager, get instance, and then I'm going to use p camera manager to get the projection. Let's see if that solved our problem. Great. So what did that just do? It created a projection matrix that took into account the size of the window. And it's doing that every single frame. Again, this is not kind of in the context of doing this stuff, but you should kind of understand that when you multiply in the vertex shader, the vertex shader isn't doing very much. It's taking in the vertices and it's applying a transformation to them, and that transformation is the combination of your projection, your view, and your model. And the three are independent. We'll talk about that more in kind of oncoming lectures. But you can kind of understand that the projection sort of takes that 3D stuff in the world and then kind of projects it onto a flat plane. And in this case, the size of your plane matters, right? If your plane is a little window or a big window, right, the image that's projected through it doesn't change, but the math certainly does. The way you project onto a small window and onto a bigger window or into a pane is different based on the sizing of that window, of the position, of so on. And that is what a perspective transformation does. And when we're not going into depth about all the parameters of projection matrix and what to change about them, but you've effectively got FOV, which is sort of the field of view. You've got the width and the height, and then effectively the aspect ratio of your pane. And those things will change it, right? If you notice, for example, if I go back to my code, instead of using the camera manager, right, it's going to look all kinds of funky and warped. And if I kind of guess, I'm guessing that my aspect ratio is something like, I don't know, like divided by 1080. What is that? It's like, yeah, 1.8-ish. right? So like, if assuming it's like about 1.8, 1.7, it's not actually, right? The numbers are not exactly, it's going to look pretty close to the previous one, right? Similarly, if I don't use the aspect ratio and instead I use something like the different perspective, so there's a perspective FOV, and now I'm using like 45 degrees FOV, and my width is going to be, yeah, like just like what I did, 1080, and the height is 1920, which is not, by the way, my screen is a 4K monitor, so it's not the absolute values, it's the relative. And this is the near plane and the far plane, which I'll talk about in a second, right? Okay. The fun part, the fun part of C++ programming and casting. That should work. Okay, maybe I'm backwards here. Right, width, height, totally backwards. Yeah, now back to normal again. So you can kind of see that these things matter. Another thing I want to kind of point out is this near plane thing. So what if I set my near plane to 2? That's going to be 2 out in front of the camera. You won't see anything, but you'll kind of see a little bit when it kind of sticks out. So what's interesting is if I have a near plane, and I'm sure you played a video game where you walk up too close to something and it gets kind of cut off. I'm going to try to replicate that here. And that's what's happening is the math, which is effectively, it's not just projecting, you're not exactly projecting it, you're taking vertices and transforming them into a different space, and that space is defined by a frustum, or kind of a trapezoidal space, but that trapezoid has a front and a back. And so what I'm going to try to do is show you what happens when things stick out the front. You'll never really see things stick out the back because they're behind you, but you'll see how it'll kind of slice through because those vertices are outside what's called clip space, and they get clipped and they never make it to the fragment shader. They'll just sort of be discarded. And that's something that's really important to note because you can use this to great effect, like slicing things and having a cool effect like that. Or it could also be a bug where if you don't set your near plane correctly, things will look really strange, and you'll have a lot of like errors. So that's sort of it. There's another thing that I would like to show you guys. There's another way to create a quad. Well, let me get rid of this annoying code here. There's another way to create a quad, and that is instead of a cube, and instead of creating a cube made up of the individual vertices, you instead create a bunch of quads in an object, and then they're rendered. Now, I'm not going to do that because it's the third way, and the third way is actually what's going to be much more aligned with models and meshes that you would load from disk than this. And so I think this is a good opportunity to do this. But this part of the video is largely elective. Watch it if you'd like. I'm probably going to kind of bumble my way through it because the syntax is a little bit annoying to get right. But let's do it. So one thing that you've noticed here, this architecture already lends itself to the fact that there are these 8 vertices, but we're pushing them into a vertex buffer a lot of times, right? You can kind of see how much data is being wasted here. It's like 1, 2, 3, 4, 5, 6 per face times 6 faces. So we've got 36 vertices, when in reality there's only 8 of them. So that's a pretty significant bump in data, right? That's what is that? You know, 4.5 times as much data as we really need to have. So there's a new thing, and we have to actually go into the mesh architecture a little bit, and it's called a index buffer, and what we can call it is MUVIO. And much like a buffer object, we're instead using another buffer to create indices. So I'm going to do my best here. And how are we going to do this? We're going to create another struct index. And it's just going to be a GLM. In fact, we could probably just do a U16 vector 2. We don't need an index. And what is a U16 vector 2, and why did it have exactly what I was looking for? That's because U stands for unsigned, 16 means a 16-bit integer, meaning like a short, and a vector 2 is a vector of these. And the reason that GLM has this particular type is because generally speaking, you don't have more than 65,000 indices or vertices in an object. But if you do, you would not want to use the 16 short, so you would want to use 32 or something like that. So just keep in mind, generally speaking, if your meshes are getting out beyond 65,000, why did I say 65,000? Right, that's the maximum value of a 16-bit thing. So if you go to the power of 16 times 1, great. So that's your maximum value. So yeah, keep that in mind if you actually do follow this and use it. Great. So now let's go back to mesh, and we want to go actually into the init here, and we want to go GL bind for in the same way that we've generated the VAO, we want to do GL gen the VBO, I mean, we want to do GL gen buffers 1 MUVIO. Great. All right, I'm going to pause the video just a second to refresh myself on some of these things so that I know the nomenclature a little bit, because this is, I think, a cool thing to share with you guys. Okay, we're back. Okay, so I'm going to go back to just missing a couple of things that I needed to kind of remember. So what we're going to do is we've generated the buffer, and then we're going to bind it to what's called the GL element array, buffer. And great. And now down here, we're going to have to set up the buffer data. And the buffer data, let's first do this for quad, because I think that's going to be a little bit easier. For a triangle, I mean. Let's do this for these other ones. You'll notice, by the way, if I run this now, it still works. For the time being. Okay, so now we've created this VIO, and what we want to do is we want to fill it in the same way that we did here. Fill index buffer, GL buffer data, just like we did before, GL element array buffer. And we actually have a very similar code to this, right? But instead of vertices, we're going to go indices, and then we're going to go GLM U16 vector 2, and then we're going to go indices, and again we're just going to go static draw as before. Now the issue is we have nothing in here, and this is, I think, where the real magic of the index buffer comes into play. So first we're going to create a GLM U16 vec2, and we can fill it with these two values. Actually, we don't even want we don't need a vec2. We just need a uint. My bad. Okay, sorry. We don't actually need a 2, we just need 1. An index is just going to be just a set of values. And so let's do this. Let's go GL uint, right? Or just do a short, unsigned short. For now. Unsigned short. What we're going to do then is we're going to m indices push back right, we're going to push back 0, 1, this will make a lot of sense in just a minute. We're going to push back 1 and 2. Doing this for the triangle example is really dumb, but it kind of exemplifies the other parts. Cool. So now we've created a index buffer. We've pushed data to it, which is 0, 1, and 2. Keep in mind we still have a vertex buffer object, and the vertex buffer object currently contains 3 vertices. Okay. Now, when we draw the triangle, this is a bit of a diversion. This is the part that will break everything else. So instead of drawing triangles like this, what we do is we GL draw elements, and then we go GL triangles, and then we go indices dot size. So now we're actually going to render the number of indices as given by the indices object, not by the number of vertices in our vertex object. And then we're going to be an unsigned short. That's the size of the element. And then we're going to be rendering at the 0 point. We're going to render immediately. So let's see what happens here. Here, let's do it this way. Let's be smart. If m indices dot size is greater than 0, we'll do it this way. Else we'll do it the old way. And let's make sure that we actually hit this code, and we can compile. You'll notice that here our indices, we have 3. So let's see what happens. And we still have a triangle. So what's really cool about this is that it's using the indices to index the vertex buffer. Notice now, because of the way we did it, if we go back to the cube, it will still work, hopefully. However, if I get rid of this if, which we want everything to be drawn with indices, more efficient that way. Generally, you're not rendering triangles, you're going to be rendering primitives or objects. And if you do this, it's going to blow up because the size is 0 and it's going to be unhappy. Okay, so how do we do that exact same thing for the quad? And I think that's going to be interesting. Let's do that for the quad. Let's go back here. I think the quad's going to be illustrative because the quad has 2 triangles, right? If we render this now, if we try to run it, we'll get nothing, just like we did before. So let's go to the quad. First, let's copy this so we have a really easy, simple thing. And you'll notice that this code is not going to mean anything anymore. We don't, what it does, we do need to push our vertices, but what we need is we need to push them immediately. Push them, vertices, push back our vertex top left, our top right, our bottom left, and our bottom right. And we no longer push them this way, but let's not forget them. Let's not do that yet. So let me comment this out. And now I'm going to push just these 3, the first 3. And notice that it's going to be, the first 3 are going to be 0, like 0 is this one, 1 is this one, and 2 is this one. So it's going to be the top left, top right, bottom left. So I don't know if we'll see anything because of the ordering of triangles, but hopefully with enough rotation, some triangle shows up. Maybe not. Okay, whatever. So we've now pushed these 3. Now it looks like the top right, top left, and bottom left, that's the way we want to go. So the top right is actually the 1. Remember, this is 0 indexed. The top left is going to be the 0. And then the bottom left is number 2. So let's see if we now see a quad, or a triangle. There you go. There's the first triangle of our quad. And now, all we have to do is the same thing for the second one. So bottom right is actually the 3rd, top right is the 2nd, and bottom left is the 3rd. Oops. Bottom left is the, bottom right, top right, bottom left is 2, top right is 1. Great. And now you can already see a little bit of an improved design just for the quad. And the quad is only just 2 triangles, right? So now we can delete this code. Okay, now let's do this for the cube. One thing, there's a nice trick here. So first off, what we need to do is we need to M vertices, push back, vertex top, left, front, right? We need to push each one of these back manually. and finally bottom right back. Another thing I like to do here is, this is a fun little trick. Unsigned short, vert count equals 0. And what we can do is we can do unsigned short. This is just for help. V top left front equals vert count plus plus. Remember that vert plus plus on the after, it means that 0 is going to be assigned to this and then incremented. And so what we can do here is we can go top left, top right front. Oops. Bottom left front, bottom right front, top left back, top right back, and then bottom left back, bottom left back, and then bottom right back. Great. These will all be sufficiently unique, hopefully. And now, instead of doing this here, so we push this code up here. And then we just create the index buffer in the same way as we did before. Let's do this. So we're going to, we don't need to cast it. So we're just going to copy these vertices from the faces, right? Okay. Let's go through it. VTRF. I'm just copying it like vertex top left front, so VTLF. Right in here, VBLF, vertex bottom left front. And what's nice too is, like, you know, copy and paste, great. BRF, TRF, BLF. Great. Now we can just delete these. And if you remember the back face, the only thing we need to change here is B, oops. No. And then we switch these guys, like we were talking about before. Great. And that's it. Let's just see if this works for these two faces. Otherwise, we want to evaluate the technique here. Because notice again, the vertex buffer is being uploaded separately than the other side. And that's cool. So it's working for the most part, it looks like. It's gonna be hard to tell. Let's simplify the rotation here just by Y. Let's make sure that we see another quad. Great. So what's really happening here is the vertex buffer memory is being put onto GPU, and then you have an index buffer that's also on GPU. And you're telling the GPU to basically use this buffer as an index into that. And you can imagine that's really, really valuable, because now you don't have to upload a vertex for every triangle. You only have to upload all the vertex data and then almost kind of connect the dots, and tell the GPU how to connect those dots by way of the vertex index buffer. And so let me quickly rinse and repeat this for the left face. So TLF, TLB, BLF, BLB, and then TLF, BLF, or BLB, BLF. Okay, TLF, TLB, BLB, TLF, BLB, BLF, right? The right face again, R, R. You can see how much easier it is to manipulate things in the index space versus the vertex space as well. Let's do this for the top. So this is TRB, TLB, TLF. TRB, TLF, TRF. Another thing I want to say is like this may not seem like super useful for quads. I mean it is, but where it's really useful are for the continuous surface or parameterized surface objects like spheres, a torus, cylinders even. You know, especially when you get into sort of more slightly different primitive types or element types like a triangle fan and strip, you can imagine you can create pretty interesting things here. So like, let's make sure that our rotation still looks good on top. And yeah, and now what's really neat about this particular example is that the vertex buffer data, oh, I'm missing I fucked up something. Let's look. Which face is broken? It's clearly one of the, I think it's the bottom one. Top is okay. And then the bottom is broken. So why is the bottom broken? TRB. Oh, because this should be B. There we go. So yeah, again, now we've got this really great kind of separation and architecture between the two. You've got geometry data in one buffer, and you've got an index buffer separately. And this also already kind of goes into some of the ideas about translation and projection, which we'll talk about in a later lecture. Well, cool guys. Hopefully this was helpful. Sorry for the split in between. The index buffer syntax was just was not on top of my mind. So pretty powerful stuff, and hopefully you can kind of already see how you would put this into practice.